Okay, cool. So we are now in lecture 11. I mean, I must confess, I was just telling right now that, I mean, the plan that I had for today's lecture turned out to be more complicated than I had originally anticipated. But I'm hoping to give you I mean, even if not all the details, like most of the details to do polynomial multiplication over general rings, which is going to be the focus of today's lecture. And besides the algorithm per se, I think the key new learning that I hope that you will gain today is the notion of sort of artificially adding elements to the ring as and when necessary. By slowly expanding your world that you work in, so that it gives you some extra power to do certain things which you couldn't do otherwise. Okay, and this notion will become more and more important as we proceed further. So, in my opinion, this is a lecture where I'm going to not really talk a lot about what this quotienting business or going modulo business is, but I want to just convince you that this makes sense. And then we will deal with quotients, etc., in a formal sense, because they will show up a lot in subsequent lectures, etc. Okay, so I just want to go over some brief recap. So the most important definition that we saw last time was this notion of what's called a principal root of unity. Okay, a principal root of unity, basically tell yourself that a principal root of unity is one that allows you to do FFT. Okay, in a sense that the definition is made in such a way that you basically want to say the inverse of the FFT matrix, I want it to be the FFT of omega inverse. That's the statement you want to make, and whatever is necessary for that statement, we'll call that a principal root of unity. And if you just look at the proof of the fact that f omega times whatever the FFT matrix of omega times FFT matrix of omega inverse equals whatever n times the identity, notice that you only use these two properties of omega. So the first thing is, of course, saying that it must be an nth root of unity. That's just saying that if I raise it to power n, I want to get 1. And the second thing is sort of saying that columns of the matrix are sort of orthogonal in some sense. Okay, so it's like saying for all I other than 0 and n, if you think of any I between 0 and n, this particular sum turns out to be equal to 0. Okay, and in general, we will basically say that a ring supports FFT n to just mean that it contains a principal nth root of unity. Because once you have that principal nth root of unity, you can talk about FFT and you can actually do the algorithm that you have. But as we mentioned last time, it might just be that you're working in a world where there are no nth roots of unities, or there are no principal nth roots of unity. Like for instance, maybe you're interested in integer polynomials. Then if anything, a root of unity can either be +1 or -1. So whenever n becomes large enough, these are not going to be principal anymore. Okay. So, but in general, we will say that R supports FFT of n to mean that it contains a principal nth root of unity. So once we have that, let me just write down the FFT algorithm that we saw. It was a very natural algorithm, and throughout I will always assume that whenever you encounter n or something, I will assume it's a power of 2. Okay, it's not particularly important as long as it's a power of a small number, or at least has a lot of factors, because this is what is going to let you do a divide and conquer. But it's just convenient to work with n being power of 2, because we'll have to do a padding once and forget about it. Okay, so what's the general setup? You are given a polynomial as a list of coefficients. These are all polynomials that come from the coefficients come from some ring. Okay, this is the world of coefficients that you have. Maybe they are integers, maybe they are rational numbers, real numbers. We don't, at this point, we are sort of indifferent to where the ring, what the ring is. As long as, along with that, I am provided what is called, I need an nth principal root of unity. I'll keep using prow just to, avoid writing principal root of unity all the time. Okay. So what is the FFT supposed to do? You think of this as your polynomial. And the goal is to evaluate this polynomial on these endpoints simultaneously. That's what you're hoping to output. That's the expected output of this algorithm. And the way we did this was we basically said, let's take our polynomial, let's split them into the odd part and the even part. I mean, so that you arrange for something like this. So all you're going to do is you're going to take all the even indices of this, put that in F even, odd indices of this, put that in F odd. That's all you're doing. Okay, so now each of them are polynomials of degree n by 2, like or are strictly smaller than n by 2. Okay, and now what was the point? The point was to let's recursively call FFT of the even part and the odd part. But again, in order for it to become for an NFFT, I needed to provide an nth principal root of unity. Now I need to provide an n by 2th principal root of unity. And fortunately, omega squared satisfies the necessary requirements for the principal. So you do the FFT, but with the root being omega squared as opposed to omega. So when you run this recursive algorithm, you will now get some list of evaluations. Okay, and in general, it will be an array of n by 2 elements coming from your ring R, because each one is supposed to be the evaluation at 1, omega squared, omega to the 4, omega to the 6, etc. So similarly, alpha is one such thing, beta is one such thing. And you just use this particular equation that you had to now write down what should the evaluation of f be on all the powers of omega. And that you basically, it's some small manipulation in terms of alpha and alpha i's, beta i's, and omega I. And you, once you compute all of them, you say, okay, this is the list of evaluations. So this was the FFT algorithm. I mean, it's sort of oblivious to what exactly this omega is. As long as omega is guaranteed to have certain properties, this is a very useful algorithm. Okay, so, and a simple sort of, just a recurrence relation as to what happens in the algorithm told you that the number of operations that you needed in order to completely write down this algorithm. By the way, I have not written the base case, but okay, ignore the base. I mean, base case is whatever, some constant thing. So we basically notice that, the FFT algorithm takes order n log n operations in R, which means the number of times you will add 2 elements in R or multiply 2 elements in R. The total number of such operations you will do is like n log n. So if you think of all operations in R as unit cost operations, then this is an n log n algorithm. Okay, but I want to be a bit I want to stare at this a bit more and be a bit more precise about what sort of operations did we end up using. Okay, so here is a question. Suppose we were to run the FFT algorithm. There are some multiplications in R we will end up doing. What do those multiplications look like? Like, I want to say, can you say that the multiplications that we will end up doing are only of a specific kind? Okay, can we make a statement of this sort? So let's just stare at the algorithm and see where all do multiplications show up here. Okay, we need to multiply stuff in order to compute all these omegas. So I start with an omega, then multiply with omega again, multiply with omega again, etc. That's what I need to do here. Splitting into F even and F odd doesn't require any multiplication. You're basically just taking the array and splitting them into the even indices and odd indices. Okay, there are some recursive calls here, but let's go further. But then the only multiplication seems to be things of the following form. So an important observation at this point is that the only multiplications that the FFT algorithm ever does is of the form you multiply a power of omega with a ring element. You never ever multiply an arbitrary ring element with some other arbitrary ring element. It just never shows up in the algorithm. Okay, and this is going to become crucial. Okay, so I want to sort of be precise, and so that when I say that order n log n operations, what I really mean is the following. This actually has two components. There are order n log n additions. I mean, of the form r plus r. Like, I have no control. I mean, like, this alpha a could be something, this could be something, I end up adding. So the additions, I don't have any control. But in terms of multiplications, there are order n log n omega power I times r mults. Okay, so I hope this is sort of clear from the algorithm description that the only multiplications that this algorithm ever does is take one of your roots of unities, which is basically generated by whatever omega was given to you, times like an arbitrary ring element. That's the only sort of multiplication that this algorithm does. So when we are going to try and expand our ring and stuff like that, we are going to try and make sure that these sort of multiplications are sort of cheap. Like multiplying with omega is somehow cheap rather than multiplying two arbitrary elements. That's what I want to focus on. Okay, good. So this is just one extra observation about what the FFT algorithm seems to do. And once you have an FFT algorithm, we now we sort of saw how you can do polynomial multiplication that is of polynomials of degree smaller than n. There are two input polynomials, f and g have degree smaller than n. And I can do this polynomial multiplication as long as R supports FFT 2n. Because we wanted to compute the product polynomial on 2n distinct points so that we can interpolate. And we were using the FFT for that process. Okay, and what was that algorithm overall? You basically said, let's do the FFT of f with respect to omega. Just want to note that this omega is a 2nth principal root of unity. Okay, so f is actually a polynomial of degree at most n, but you can pretend that it's a polynomial of degree at most 2n by putting zeros. Right? So you first compute alpha bar, which is the FFT of f. I should keep saying DFT of f, the discrete Fourier transform. FFT is one algorithm to do that. That's it. But it doesn't matter. So you do it for alpha, for f, you do it for g. Notice that both of them are now going to be some array of 2n coefficients. Okay. And what is your gamma supposed to be? You just take a pointwise product. Okay. That's going to be the evaluation of h at various points. And now you do an inverse FFT and you need to divide by 1 over 2n. Sorry, you need to divide by 2n because of that extra whatever nonsense was happening. Okay, and that was the algorithm. And therefore, we basically said that this was, I should have said written, these were these many operations in R. Okay, once again, let's be precise. I want to exactly know what sort of additions are we doing, what sort of multiplications are we doing, etc. I want to be precise about that. Okay, so I'm going to split this into 3 parts. The additions, I sort of don't care. N log n additions. This is of the form, I don't know, arbitrary element of R plus an arbitrary element of R. Okay, and each of these FFTs, we just observed that the only multiplication that is does are things of the form a power of a root of unity times an arbitrary element of R. So there are going to be order n log n, whatever, omega power I times R mults. Okay, plus there are these multiplications. Alpha is going to be some set of 2n things. Beta is going to be some set of 2n things. And you are going to do a component-wise multiplication. So this is one instance when you actually have 2n times R cross R mults. Okay. The rest of it is like, this is again, it goes into these two. This I'm just going to assume is like not much at all. Okay, so the point I'm trying to make is that in the FFT setup, they never did multiplications of the form an arbitrary element of R times an arbitrary element of R. Whereas in the polynomial multiplication setup, even though the total number of operations was n log n, only 2n of those seemed like an arbitrary element of R times an arbitrary element of R. Okay, so I hope this is clear. I mean, if there are any questions here, maybe this is a good time to make sure we're all on the same page, because we're going to try and exploit this as we sort of make our ring bigger, etc.
Can you repeat the part for the omega to the power I cross R?
So, okay, so let's look at this FFT algorithm. And I just want to say that previously we were saying there are n log n operations. We didn't particularly pay attention to what these operations look like. But I'm just saying, if you stare at this algorithm, you notice that the only sort of multiplications you ever do in this algorithm are things of the form you multiply some power of omega with an arbitrary ring element. Okay, so therefore, all the multiplications that show up in this FFT algorithm are all multiplications of the form some power of omega times an arbitrary element of R. Like there are no, I don't know, like bizarre multiplications in the FFT algorithm at all. Okay. And once we had this, we looked at the polynomial multiplication algorithm and noticed that it's mostly the FFT multiplications, plus we have one extra bunch of multiplications, but there are only 2n of them. Even though the total number of operations you did in R was like order n log n, the number of R times R multiplications that were not of the form omega power I times R, they're only 2n of them, because that comes only from this step. Did that make sense?
Yeah.
Okay. Okay, good. So this is what we are going to pay attention to. And notice that last time we had also said, I didn't present a proof in class, but I added it in the notes, which is that a sufficient condition for a particular element to be a principal 2nth root of unity, where again n is a power of 2, is that if it so happens that omega power n is minus 1, or rather omega power n plus 1 equals 0, then it turns out that such an omega is always a 2nth principal root of it. Okay, so I mean, I just thought I'll maybe ask this. So suppose you wanted to make a statement of this form. You wanted to come up with a sufficient condition for something being a 3nth root of unity where n is a power of 3. Okay, so how would you replace this in this blank? I mean, you don't need to prove it, but do you have a guess of what you would want to do?
I think I got a bit lost. So what are we trying to do?
So we are trying to come up. So previously we wanted to say you are looking for a 2nth root of unity where n was a power of 2. Okay.
So
we said this is a sufficient condition. If omega n plus 1 equals 0, then omega is definitely going to be a 2nth principal root of unity. But now suppose, let's say you're working with powers of 3. I mean, just as like a hypothetical situation. And you somehow want to say that you want to replace this condition by some other condition, which I put as a dash, okay, as a blank, such that if that condition were true, I want to claim that it must be a 3nth principal root of
it. Right. Like something 1 plus omega or something.
So in some sense, so let me just rewrite this to sort of say omega power n plus 1 equals 0. Intuitively, the reason why this shows up is the following. See, if you want eventually omega to be a 2nth root of unity, which means omega should certainly be a solution to omega power 2n minus 1 equals 0.
So we will only take.
Okay, now we'll.
So we need to only take omega to the power 2n, right?
Sorry.
At the induction. So for the case of 2, we are looking at omega to the power n plus 1 equal to 0. So technically, if we have that, then we will look at only omega to the power 2n plus 1 equal to 0 to say that omega is a 3nth root of unity. right?
I don't see why that is happening. But maybe let me try to give you a little bit of hint. Okay, so this is omega power 2n minus 1. And notice that this factorizes as omega power n plus 1 into omega power n minus 1. So in some sense, if omega satisfies this equation, I mean, I'm being very hand-wavy here, but just trying to give some intuition, then it feels like either this must be 0 or this must be 0. But on the other hand, if this was equal to 0, it doesn't feel like a 2nth root of unity. It feels like an nth root of unity. So it just feels like, okay, these things correspond to all those roots of unities, which are not what you want. The things that you want are all here in some sense. Yeah, I mean, this is a very hand-wavy statement, but hopefully it's trying to make sense. Okay, now can you guess what this blank should be?
Yeah, sure. It should be probably this omega to the n plus 1 plus 3 omega. Like, no, sorry. What?
So you basically need to be doing this, right? Omega
1.
power 3n minus 1 divided by omega power n minus 1.
Yeah, this would be
so this is omega power 2n
1
plus omega power n plus 1.
Plus 1.
Sure. Okay. Oh, right.
Okay.
Right. X square plus y square plus AB.
Yeah. So you can verify that this actually works, but hopefully you get some intuition as to why you are expecting this or something. Okay, even though this wasn't a formal proof by any sense, but I'm just trying to somehow demystify this condition that was there. Okay, so let's proceed. Now I want to talk about this notion of adjoining elements. This is the thing of, we are trying to do, we want to do FFT to do polynomial multiplication. For that, we need a root of unity, but maybe our ring does not have a root of unity, and we are somehow trying to artificially add one such element to it. Okay, and without getting into too much formalism, I'm just going to get you familiar with this operation, because this is something that you have done in other contexts. You probably just didn't give a name to it. Okay, and we'll just work with this sort of slightly vaguish way of dealing with this to a point where you're convinced that this ought to work, and then we'll formalize it towards the end of the lecture and maybe in the next lecture. Okay, so like I mentioned last time, we always work with these complex numbers. I mean, this is something that we are familiar with, but I want to say the complex numbers are no different from some, some object of this type. And I'm going to somehow, at the moment, I'm just basically going to tell myself, what are things here? These are things of the form a plus b times t, where a and b happen to be real numbers. And I'm mentally telling myself that every time I see t squared, I'm going to replace it with minus 1. Because in this world, t squared plus 1 equals 0. Okay, that's my mental picture. I mean, t is playing the role of I that we usually put in complex numbers. Okay. Now, the nice thing is you can always add two such elements. If I give you a plus bt and c plus dt, you just add a plus c and b plus d. So that is clear. But somehow I want to also say that I want to be able to multiply things together. So if I have a plus bt and multiply with c plus dt, for the moment, let me ignore the fact that t squared equals minus 1 and just multiply them like normally. So I get some expression of this sort. But once I have this expression, I notice a t squared. And now I can tell myself, aha, every time I see t squared, I'm supposed to replace it with minus 1. Okay. So we will say this is equal to AC minus BD plus AD plus BC times T. Okay. And I'm going to basically write down a weird thing, which is say this is modulo the relation t squared plus 1 equals 0. This is like saying if you believe t squared is equal to minus 1, then wherever you see t squared, I'm replacing it with minus 1. That's it. Just think of it as a syntactic operation. Okay. And this is exactly what you would have written when you multiply two complex numbers. And all I'm saying is that you can interpret this without knowing that, I is actually a complex number or whatever, and just think of I as being a symbol. And just saying when you multiply it and whenever you encounter a t squared, just replace it with -1. Okay, it's just some syntactic way of multiplying elements of this type. I'm telling you how to add things, I'm telling you how to multiply things. So therefore, this is a ring, whatever that thing is. Okay, so let's do one other
Your
example.
voice is breaking.
Sorry?
Is your voice is breaking or it's my internet issue?
I have no idea. It's my connection seems to be okay. Is it okay for others?
What happened? I'm hearing everything.
Okay.
Okay, then my
Okay. So now let's do the following. Let's just imagine our ring was the rationals. I mean, this is the rationals we are familiar with. But for some stupid reason, suppose we want the cube root of 5 in it. No, something. I mean, like I somehow want the cube root of 5. So I'm just going to think of t as corresponding to the fact that t equals cube root of 5. And mentally, the relation I'm thinking of is whenever I see t cubed, I want to replace this with 5. Okay, like that's this is the world I want to work in. So let's just do the following. Suppose I expanded, what would I get? I will get 1 plus 4 cube root of 5 plus 6 cube root of 5 the whole squared plus 6 cube root of 5 the whole cube plus am I missing something? Sorry, this is just going to be 4, right? And then cube root of 5 the whole power 4. Okay, and so how would I simplify this? I will write this as 1 plus 4 times cube root of 5 plus 6 times cube root of 5 squared plus now suddenly I look at cube root of 5 the whole cube. So I immediately know for a fact that I should be replacing it with 5. So I write it as 4 times 5 plus this looks like it's a cube root of 5 whole cube times a cube root of 5. Okay, so I can write this as 5 times cube root of 5. Okay, and this is again, this equality is modulo cube root of 5 the whole cube equals 5. I mean, under that relation, you just replace any occurrence of a cube root of 5 whole cube you had in this expression by whatever you need to, and yeah, you'll get something. Okay, so you'll get some expression of this form. But so I think I seem to have made a mistake. It should have been 14641. Okay, so this is some expression that you will get, but you could have done exactly the same thing by just thinking of t as being a formal variable. And whenever you see t cube or something, you just make these changes. Okay, so what are the relations I want to say? Whenever I see t cube, I'm supposed to replace it by 5. Which means whenever I see a t power 4, I'm supposed to replace by 5t. And whenever I see a t power 5, I'm going to replace it by 5t squared. And when I see a t power 6, I'm going to replace it by 5 into 5, which is 25, etc., etc. Okay, so you just take this expression and replace t cube by 5 and t power 4 by 5t, you will basically end up with what you started. So all I'm trying to say is that saying that you're working with cube root of 5 is no different from saying that you're working with qt quotiented with t power 5 minus 5. Okay, so just trying to get you familiar with what expressions like this mean without really going into too much details here. Okay, as long as you are convinced. So sorry, yeah, go ahead.
No, I mean, I had one. I mean, this might be a digression, but either now or maybe at the end of the class, I was just curious. So we are doing this, like we are looking at this basically like polynomials over this ring and then quotiented with something. And just wanted to know what what is this geometrically saying? Like, are we it is saying something geometrically? But
it is, but maybe I'll come to it towards the end. I mean, like, depending on how much ground we cover today, either we'll do it today or we'll do it in the next lecture. Okay, so there is a general way in which you can start off with one ring and create other rings by this operation called quotienting. And right now, I'm just giving you a sense of what quotienting means, just to a level of, as long as you're able to manipulate things well, we are done. We don't need to bother too much about it. Oh, sorry, this is not t power 5 minus 5. This should have been t cube minus 5. Okay, so this is the same thing as expressions of the form a plus bt plus ct squared, where a, b, and c happen to be rational numbers, where you add stuff as usual, and when you multiply stuff, whenever you encounter terms of this thing, make the corresponding substitutions. That's all it means. Okay, I'm just artificially creating these weird objects in which you can add, multiply, and so on. But these are weird objects that somehow seem to contain the sort of elements you're looking for. You just manufactured one such element in your space. So that's what we are going to do. Okay, so what I'm going to do is, now when you say, I want to multiply 2 degree 4 polynomials. In order to multiply 2 degree 4 polynomials, had I had a 8th root of unity or 8th principal root of unity, I could have done the FFT process. But maybe I'm working with the rational numbers. The world I work in does not have an 8th root of unity. So let's artificially create one. So we are instead going to work with like the Q, where you adjoint a T with the relation t power 4 plus 1 equals 0. Okay, and formally, what is this? These are all expressions of this type, like we wrote above. It's just a plus bt plus ct squared plus dt cubed, where a, b, c, and d are rational numbers. You add stuff as usual, and whenever you multiply stuff, if you encounter things of this type, you make the corresponding substitution. This is exactly like you would have multiplied complex numbers and so on. It's just now you have a few more terms. That's about it. So are things clear so far? I mean, just what this world means. Okay. So it's just that I'm just telling you one of these new rings, these sort of weird rings that are there, that has just the additional property that, I'm just telling you that here is how you add things, here is how you multiply things. And the ring is constructed in such a way that the element t, which corresponds to 0 plus 1 times t plus 0 times t squared plus 0 times t cubed, that satisfies the relation t power 4 plus 1 equals 0. Just by definition, by construction. So somehow the t that you manage to add to this new world is one of the 8th roots, principal roots of unities that you were looking for. Okay, this is how you adjoin a new element to whatever ring you're starting off with. Okay, cool. So now, once we have this, we can now start describing how would you go about multiplying polynomials over general rings, which maybe does not have the root of unity that you're looking for. Okay, just think of R as being, I don't know, say maybe the rational numbers. Okay, you're looking for a 2nth principal root of unity. Well, there is no such thing. So we need to cook up a 2nth root of unity somehow into this world. Okay, and like always, I'm always going to assume that this n is a power of 2. Okay, so what am I going to do? I'm going to say, let's instead work in this new world, R prime, which is going to be qt divided by t power n plus 1. Okay, and what is this? This is just set of expressions of the form a0 plus a1t plus blah, 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 plus a n minus 1 t power n minus 1, where all of these ai's come from the old world, whatever was the base ring in some sense, and you add and multiply stuff properly. appropriately. Okay, and the key point, the reason for doing this is that here is an element which is this element t, which is now present in my world of coefficients. Okay, if I call that by omega, is our 2nth root of unity. Whatever, principal root of. Okay, it's like as if you artificially added an element. Like for instance, if you wanted to work with the fourth root of unity, you would have wanted to add I to this because I know that I squared equals -1. So I happens to be a fourth root of unity. So that's mentally you will tell yourself, okay, let's go to the complex numbers and work with things. And here instead saying you don't need to go all the way to complex numbers, you need to go till whatever this world is. Okay, now that we have this, let's just do the following. So what do we have right now? Oh, this is so originally I was given f and g as a list of coefficients. Okay, so therefore it's made up of whatever n coefficients, each of which happen to be rational numbers. But I might as well consider them as n coefficients where each of them are sort of complex numbers, right? Just like saying that every element that is from the base field can also be thought of as an element in this field where you're just setting a1, a2 all the way to the other thing to be equal to 0. You're putting whatever you want in just a0. So addition and multiplication is as you would expect. So whatever f and g are provided, I might as well assume that I'm given a bunch of coefficients, each of which come from the ring R prime instead of the rational numbers. Okay. Now the task now boils down to, I have two polynomials in R prime of x. Can I multiply them together? Okay. And we just saw that if you want to multiply two polynomials that whose coefficients come from some ring, if that ring happens to have a 2nth principal root of unity, you could do the FFT based multiplication. And that's what we are going to do. We'll just run the FFT with respect to R prime, where we'll provide this omega equal to t as the root. And we will run the FFT with respect to R prime on G, where we provide omega as the root. Now we'll get alpha and beta. We will do the same multiplication like we did last time. And then we will do the inverse FFT, and then we will divide. Like it's as if, you know, R prime is currently some world that has a root of unity. We are just going to run the algorithm we already have. Okay, are there any questions so far? Is the overall idea clear? We still need to analyze this algorithm. But are you at least convinced of what the algorithm is doing? Okay, there's nothing too fancy that's going on here. In order to run the FFT, you needed an omega. You somehow artificially created a world that has this omega, and you're pretending to do multiplication in this world as opposed to the original world. It's like saying somebody gave you two real polynomials. Instead of multiplying them as real polynomials, you interpreted them as complex polynomials and multiplied them together. So that's basically what you're doing. Okay, now let's start to analyze this. Okay, what is the running time? How much time did we end up taking? There were two FFT calls over this manufactured ring R prime. Okay, plus these were all multiplications of the form R prime times something in R prime. There were multiplications of an arbitrary element, I have no control over it, and some other arbitrary element, plus some extra order n operations, maybe for this division or whatever. I mean, some extra, just splitting them into evens and odds and stuff like that. Some minor extra bookkeeping stuff we perhaps need. Okay, but of course, I have no library that is going to do addition and multiplication over R prime. Or the only thing I know is I am told that multiplying two rational numbers or adding two rational numbers is a unit cost operation. I somehow need to therefore count how many basic operations did I end up using. right? Because I mean, this R prime was something that we created, we manufactured at this point, right?
Okay.
Yeah.
Sorry, maybe I'm forgetting something.
Uh-huh.
What about, and are we including this the H tilde FFT computation?
Yeah, so that was this thing. Oh, sorry, this should have been 3, I guess. Yeah, sorry. Not necessarily n by 2. I'm just going to put n here. Okay, there are 3 FFT computations. Okay, one for F, one for G, and one for this H tilde. Okay, plus I have these multiplications over R prime. Did this answer your question, Varun?
Yeah, no, but wait, the T, I mean, if it's still n, like I'm
No. So this is time taken to multiply, but this is time
and this
taken
is
for
just the FFT
FFT.
computation. Yeah.
Okay, so this is what we have. And now I want to open this up and say that, okay, this is the FFT computation will sort of say that it requires n log n operations over n R prime. No, but that I want to be a bit more specific here. So what is the FFT computation going to take? This is going to say there are n log n operations in R prime, okay, plus order n R prime cross R prime multiplications. Okay, and now let's ask ourselves, okay, the simplest operation in R prime is maybe just addition. Okay, suppose I give you 2 elements in this ring R prime and I ask you to add them. How many additions over rational numbers will you need for that?
Possibly n, right?
Right, because it seems like I need to add each of the coordinates and so on and figure out what this new sum is going to be. So therefore, each operation in R prime is potentially equal to n operations in over the base in Q. And like, we are not even going there because this is already terrible. I mean, the high school multiplication that we were doing appears to be better because that took only n squared operations. So we did all this fancy adding the root of unity, etc., and don't seem to be gaining anything. Okay, so this is not quite, I mean, like we need one extra ID. Okay, but I just want to make sure, is the overall structure of what we are trying to do clear? Because if not, I'll spend more time on this because now we are just going to add some extra tricks. I mean, this is the cool algorithm of Schönhage-Strassen that we're going to see next. But I hope the overall idea is clear. We basically wanted to do FFT-based polynomial multiplications. We didn't have a root of unity, so we artificially added one. So now we are working in a new world. And in this new world, we can do FFT-based polynomial multiplication. Except that will tell me that it will take n log n additions and multiplications in this new world. But I can't tolerate n log n additions in this new world because that itself seems to be taking something like n squared log n operations in the rational numbers. Okay, but at least the overall structure is that, okay, I want to do polynomial based FFT based multiplication. So we are adding a root of unity. It's just that currently the world is too big. I mean, it's like, you know, there are too many coefficients that even additions there appear to be expensive. And we don't want to spend as much time. Okay, and here comes the cool idea of Schönhage-Strassen. Okay, it's to somehow try and trade off degree for the size of this world. Okay, so basically what we are going to do is the following. Let's say this is the polynomial f that was given to me, which is a bunch of coefficients. Okay, we are going to do something very similar to what we did in the Toom-Cook algorithm, which is to split f into a bunch of blocks. And I'm going to split them into k blocks, where k is something we will choose soon. Okay, so I'm going to write this as capital F0, plus capital F1 times x power k. Sorry, not x power k. I want the size. What do I want? I want the size of each block to be, number of blocks to be k. So I'll call this, let's say, x power m plus f2 x power 2m plus fk minus 1 x power k minus 1 times m, such that k times m is equal to n. Okay, this is like saying, let's look at the first m, or whatever, the first m coefficients, put that inside f0. The next m coefficients, put that as f1. The next m thing, put that as f2, etc. So we basically broke this up into k such blocks, each of size m, so that overall km equals n. Okay, and I'm going to think of this as some bivariate polynomial of the form x comma y, where what you have done is replaced y equals x power m in this above expression. Okay, so this bivariate polynomial is just equal to f0 of x plus f1 of x times y plus f2 of x times y squared plus blah blah blah. Okay, and it's just that if you substitute y equals x power m, you get back the original polynomial. So far, nothing fancy has happened. Okay, we are just grouping terms differently and just interpreting our polynomial as instead being a bivariate polynomial instead of a single variate. Okay, let's just set up a few things. The degree in x of f tilde is the largest possible degree of any of these capital Fi's. Okay, and the largest possible degree was m minus 1. So therefore, the degree in x is like at most strictly smaller than m. The degree in y is basically whatever, k minus 1. Is this clear so far? I mean, so it's just, we are just slightly reinterpreting things. And here is the, I mean, it feels obvious at this point, but okay. So now, rather than multiplying f and g, which were two input polynomials, suppose you came up with a way of multiplying f tilde and g tilde somehow. Okay, then you can take the product polynomial and then make the substitution y equal to x power m to get back whatever you want. Is this okay? I mean, so the only thing we are saying at this point is that I know f equals f tilde of x comma x power m. Similarly, we will write down a g tilde. So f tilde times g tilde is some bivariate polynomial. And in that bivariate polynomial, had I substituted y equals x power m, I will recover whatever my f times g was. Okay, what's the gain here? What have we gained in the process? Okay, the key point is that if you think of these as, let's say, if you focus on any one variable, x or y, whatever you want, the degree of this polynomial in that corresponding variable is substantially smaller than n. Like just imagine a setting where both k and m are equal to something like root n. So normally for FFT, you would have needed a, I don't know, a 2nth root of unity. Now you only need a 2 root nth root of unity. That's going to be the gain. You're somehow trying to make sure that your world is not as large as it was last time, but you're going to adjoin to a smaller world. Okay, so let's go over this thing. F tilde is an expression of this sort. G tilde is an expression of this sort. I'm just going to forget everything and just think of it as saying, hey, this is a polynomial in y where the coefficients are these things. Where are the coefficients coming from? They are coming from this world. Each coefficient is actually a univariate polynomial in x. Okay, that's the world of coefficients right now. I have two polynomials, f tilde and g tilde, and my goal is to multiply these two together. Okay, so I want to compute an h tilde of x comma y. Let's just write this as h0 plus h1y plus all the way until what? It will be something like 2k minus 2 y power 2k minus 2. Okay. So what do I know about h tilde this thing? The degree in x, each of these terms is some product of two such whatever f5 gjs sort of a thing. Each of them had degree m. So each of these terms have degree at most 2m. And in terms of degree in y, the degree is at most 2k. It's actually 2k minus 1, but it's strictly smaller than 2k minus 1, but we're just putting it as 2k. Okay, so therefore now the task is sort of clear. We'll basically say interpret. Okay. Oh, sorry, I should have added one more thing. And so at this point, if I want to just multiply f tilde and g tilde, what is the root of unity I will need? How high should that root of unity be?
2k.
Right, because these are polynomials of degree strictly smaller than k over some ring. I don't care what this ring is. Okay, but had that ring had a 2kth root of unity, we can compute this product using using the FFT based polynomial multiplication. Okay, so what I'm going to do is I'm now going to work in this new world R prime, which is equal to Rx quotiented by x power what do I want? I need a 2kth root of unity. So one second. I'm messing up something here.
So x to the k plus 1.
So this has to be x to the k plus 1, right?
Right.
So actually I'm going to do something a little stupid. I'm going to work with x to the 2k plus 1. Okay, the reason should become clear soon. Okay, I just want to make sure. Okay, so instead, let me do the following. I'll just write down something and then we'll make it clear. This is the part that always confuses me. And I'm going to work under a world of this form. Sorry. Okay, Rx quotiented by x power 2m plus 1. And let me tell you why I am working with this world. So each of these h0, h1, blah, 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 till h2k minus 1, they are all polynomials in x of degree strictly smaller than 2m. So either I can think of them as honest to God polynomials with coefficients coming from R, but I can also think of them as polynomials that are living in this world, because in some sense there is no such substitution that you're doing. It's almost like saying that you're looking at an integer which was promised to be less than 100. But had I thought of this integer modulo 200, nothing really changes. Okay, so in some sense, I'm just taking the relations I'm taking don't affect each of these h0, h1, blah, 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 till h2k plus 1. Okay, and let's hope that this so in this world, x is going to be a 4mth root of unity. Okay, so if we set it up such that if 4m is at least as large as 2k, okay, then we can interpret f tilde and g tilde as elements of R prime of y instead, okay, and multiply them. Multiply them using FFT. Okay, so what we are doing is at the moment f tilde and g tilde were honest bivariate polynomials with rational coefficients. Let's instead think of them as bivariate polynomials where the whatever x satisfies the relation x power 2m plus 1 equal to 0. You are never ever going to even discover x power 2m when you multiply these two things. So this relation at the moment is meaningless. But the key point is that working in this world tells you that x is a 4mth root of unity. So as long as 4m was bigger than 2k, we can just do an FFT based multiplication. Okay, this is a little messy, but this is what Strassen-Schönhage's algorithm is. So what we are going to do is we are basically going to let both k and m to be equal to like root m. Okay, so let m be equal to 2 power whatever the floor of L by 2 and k equals to 2 power the ceiling of L by 2. So that you always ensure this property holds. Okay, and let me just write down the algorithm, and we'll just see an example run of this algorithm on Sage to just convince yourself as to what exactly is happening. Okay, so here is the algorithm that we have, which is that we're going to compute the bivariate polynomials f tilde and g tilde such that the original polynomials f and g you can get back from f tilde and g tilde by substituting y equal to x prime. Okay, now we'll interpret f tilde and g tilde as elements of R prime of this, where R prime is this thing. In this world, omega equal to x is a 2mth root of unity. Sorry, 4mth root of unity. Okay, so notice that this 2k will either, I mean, depending on how we set things up, you can recover a root of unity from this x. Maybe you will have to look at x squared or something of this sort, depending on what you have. And you now just use the polynomial multiplication with this root of unity and multiply these two polynomials f tilde and g tilde. You will end up with some h tilde right now. And in h tilde, you make the substitution. Okay, that's it. So this is the Strassen and Schönhage's algorithm. We'll have to do the running time analysis, but before that, I think it is useful to just maybe look at one demo, because there's a lot of steps that are going on here. So it might be good to actually see a demo of what is going on. So let me share my screen and hope that it's visible. So is my screen visible? Some Sage notebook?
Yeah.
Okay. So, I mean, I just wrote down some FFT algorithm or something. Let's not worry about that. Okay. So there is one function that I wrote down, which is polynomial multiplication if you know a root of unity. Okay. And it basically does what you expect. You compute the FFT, you compute the FFT of G, multiply them pointwise, compute the inverse FFT, and then divide. So there's nothing fancy going on here. But the interesting part, let's just do an example. So let's say these are the two polynomials we wish to multiply. So it's 1 plus 2x minus x squared plus 4x cubed, and 7 minus 2x plus 0 plus 3x cubed. Okay, so the expression is this, and if I want to write this as f tilde, you just group terms, and wherever you see an x squared, I'm putting a y instead. So this is my f tilde and this is my g tilde. So instead of multiplying f and g, we are instead going to try and multiply f tilde and g tilde. Okay, and eventually substitute y equals x squared. So I hope things are clear so far. Okay, so this is what my f tilde is, this is what my g tilde is. I'm just writing it as a list of coefficients because my FFT, whatever, the subroutine that I wrote above needs a list of coefficients. So this is the constant term, 1 plus 2x, and this is the coefficient of y. And this is the constant term, and this is the coefficient of y for f and g separately. Okay. So now what we are going to do is, what do we need to do? These are two polynomials in y of degree 1, and it is strictly less than degree 2. Which means if I want to use an FFT based multiplication, I need a 4th root of unity. And we are expanding the ring to something a little more than we want. We are going to look at x power 4 plus 1, where x is now going to be an 8th root of unity. If x is an 8th root of unity, then x squared is a 4th root of unity. So that's the omega we are going to use. Are things okay so far? Okay, I'm hoping it's fine. So now what we do is the following. So we're basically going to say, let's interpret the f tilde and g tilde that we wrote above as elements in this quotient ring. By just thinking of there being a relation, whenever you see x power 4, replace it by 1. Well, there is no x power 4. There's not even an x squared, etc. So nothing needs to be replaced. But nevertheless, I'm just going to write f tilde bar is the representation of f tilde in this new world. And g tilde bar is the representation of g tilde in this new world. So Sage puts a bar just to say that you are in a different world. You're not what you started off with. But basically, there's no change. Earlier, this used to be whatever, 4xy plus 2 minus y plus 1. Where was that? Yeah, so this is what the 4xy plus, I mean, if you do the calculation, that's what you end up getting. And it's the same thing, except you're in the bar world in some sense. Okay. Now, in this world, omega equal to x squared is your whatever 4th root of unity that you wanted. And you use that to multiply f tilde and g tilde. So now you get some h tilde, which is some weird coefficient. And then eventually I'm substituting y equal to x squared in h tilde, just to convince yourself that f times g is indeed equal to whatever we are computing in the problem. So, I mean, there's a lot of changing perspectives that are happening in the Strassen-Schönhage algorithm. But there's nothing like too crazy. It's just that one needs to convince ourselves that doing a multiplication in a slightly different world and interpreting that as a multiplication in the original world does not change the answer. Okay, so I mean, I'll share this Sage notebook at the end of the class, and maybe you can just try this out for other examples to hopefully convince yourself of what's happening. Okay, okay, so let me go back to the notes, because I mean, right now we have just said what the algorithm is, but I haven't told you. I haven't told you how to analyze it, and it's the analysis that's tricky. I mean, analysis is also tricky. Okay, so here was the algorithm. We started off with our original polynomial and computed these bivariate polynomials. And then we interpreted them in this new world, did the FFT based polynomial multiplication, and then finally substituted things. Okay, so this is the overall algorithm. So let's just ask ourselves, how much time did we end up taking overall? We are eventually multiplying two polynomials of degree f tilde and g tilde were polynomials of degree k, degree smaller than k. So therefore, based off our previous understanding, this takes k log k additions in R prime, okay, plus order k log k mults of the form omega per I times R prime, plus, to be very precise, 2k mults of the form R prime cross R prime. Okay, plus some extra stuff, which is to just, maybe compute, I mean, break this up and so on, which I'm just ignoring because that doesn't take much. Okay, but what we want to do is we want to translate all of them into how many operations over the rational numbers did you end up using? Because R prime was something that we created. So can someone tell me how much time will it take to do one addition in R prime? Notice R prime is this. So every element of R prime, you can think of it as just a polynomial in X that has 2m minus 1 2m coefficients. So if you want to add two such elements, how much time would you take per addition?
Will take 2m steps.
So it will take 2m times whatever. So the first one is going to become something like order mk log n, log k. Okay, the 2 etc. I'm just adding into that order notation, ignoring that. Okay, this is this many additions in the base field R, I mean base ring R. Just think of the base ring as maybe just the rational numbers or something. Okay, now comes the next part. How much time does it take to multiply one of these ring elements with some x power I? Because all of our omega power i's look like some x power something else. So suppose I gave you an expression of the form 1 plus 4x plus 5x squared, and I want to multiply by x cubed. I mean, it almost looks like, you just take this array and you're shifting the array by whatever amount, right? And if it overflows beyond 2m, it's a question of whether you replace it with +1 or -1 or something, because x power 2m is -1 and so on. So in some sense, multiplying by x power I is super, super cheap. So it actually only takes order m steps to do one such multiplication, because you might have to shift this thing, I mean, each of the m coefficients to some other place. Is that okay? I mean, I hope this part is okay. We're just using the fact that omega here turns out to be x, and multiplying by omega is actually turning out to be quite cheap. Okay, so therefore, this is going to again be order mk log k. Mults. In fact, it's not even mults, it's just shifting. So I'm just going to say this much time. You're just writing that particular coefficients at one other place. Okay, and now comes the tricky part. How do you multiply two arbitrary elements in this thing? I give you two such elements and I ask you to multiply them. How would you go about doing that? So, okay, let's assume you didn't have this. Suppose you didn't have this thing of having to go modulo x power 2m plus 1. Suppose I gave you two arbitrary elements and I asked you to take a product of them. Notice these are both polynomials of degree at most m, whose coefficient, or at most 2m, whose coefficients come from the base ring of coefficients. So it feels like we can recursively just apply the same algorithm. Whatever we are doing is to multiply two degree n polynomials. Now, instead of doing that, I have to multiply actually two degree 2m polynomials. Maybe after that, do some manipulation, but it feels like the multiplication is something that you can recursively apply. Okay, so this turns out to be 2k times t of 2m operations in R. Okay, we are just recursively, instead of each of these multiplications of the form r prime cross r prime, we basically say the first element is some polynomial of degree smaller than 2m, the second is some polynomial of degree smaller than 2m, and we are just going to recursively call the multiplication algorithms. After that, we'll have to make these substitutions. Whenever we see x power 2m, replace it with -1, etc. But that's a cheap thing to do. So the harder part is to multiply the two together, and that we'll recursively call this up. Okay. So, and turns out, if you actually compute this whatever recurrence, okay, so you end up with order of n log n log n times a weird thing which is called where log star of n is this really slow growing function, where it's the number of times you need to take log before, I mean, for the number to drop to less than 1. Okay, so for example, if your number is 32, if I take one log, I end up with 5. And if I take another log, I end up with some 2 point something. And if I take another log, I end up with 1 point something. And the fourth log, I'm going to end up with something less than. Okay. And it's just that even if your number is 2 power 32, you're basically going to just be one more than whatever it was for 32. So in some sense, if you want to write a power, like a tower of twos, like 2 power 2 power 2 power 2 power 2, it's the length of this tower that it needs to be for it to exceed your number n. That's what log star is. So for all practical purposes, log star of n is a constant. Okay. And so if you did this entire calculation, you end up with a running time that looks like this. Okay. And Strassen and Schönhage, this is Strassen and Schönhage's algorithm, where they added one more trick to this thing. And this trick is to replace this 2k with a k. Okay, if you somehow manage to replace the 2k with a k, you get rid of this 2 to the order log star n factor. And then you end up with an algorithm that runs in time n log n log log n. Okay, so this is the Strassen and Schönhage's algorithm. I am hoping to write down a full exposition of the Strassen-Schönhage algorithm, because I mean, somehow there aren't too many lecture notes that go into the detail in its entirety. And I must also mention that in the 2017 offering of the course, I somehow had hand waved in the lecture notes and said that this recurrence solves to n log n log log n, which is just not true. It's because, I mean, you end up with this one additional factor of 2 to the order log star n, but I'm hoping to completely write down this exposition at some point. And it's also one of these things that the original paper is in German. So I'm hoping that some new, some exposition of it will be helpful to completely understand how this thing works. So this basically says that polynomial multiplication over any ring is is basically, you can do it in order n log n log log n. I mean, if your ring already supports FFT of the appropriate degree, then you don't even need this extra factor of log log n. The extra factor of log log n is only because you are artificially expanding your world, working in that world, and then counting operations in the base world. So that's what the Schönhage-Strassen algorithm eventually is. Okay. This is a sort of tricky algorithm, but I think it's good to know. And I mean, maybe before we spend a little more time to look at what these quotients are, etc., I just want to get a sense of, do people understand the overall idea of what is happening? I mean, a large part of this algorithm is really changing the worlds that you live in. It's like you're interpreting a polynomial over some world as a polynomial in some other world and doing the operation. Previously, we said that we wanted a root of unity, so let's work with complex numbers. And this algorithm is just being a bit more precise about how large a world do you need to go into so that you can do your FFT-based multiplication. Complex numbers is an overkill. You really just need your root of unity. So you can artificially add that to your world and then do your multiplication. Okay, so in the remaining about 10 minutes that I have, I'm just going to give you a little bit of description of what these quotients are in general. Okay, but we'll do more of this in the next lecture and so on. And I also try to put up some quizzes on Academy to just get familiar with the notion of quotients and stuff. Okay, so this is going to be a complete change of gears, and we're just going to try and formalize this notion of what does it mean to say you're looking at a ring modulo blah. Okay, so what does that mean? Okay, so before we do that, I think it's good to always, whenever you deal with some new math structure, one of these structured objects that you have, like groups or vector spaces, etc., it often makes sense to try and understand what do maps between these rings look like? Like, what are the sort of maps between rings you would be interested in? And what are kernels of those maps? Okay, just like whenever you have a linear space, you often start talking about linear transformations and the null space in some sense. And this in general is always very insightful when you're dealing with any sort of structured objects. Okay, so suppose suppose R and S are two rings, and I want to say phi is an interesting map that is going from R to S. What would you like phi to satisfy? So one of the things seems to be that, suppose for instance you have an expression of the form R1 R2 minus R3, and I want to know what is the image under phi. I mean, it feels like you would like to say that this is equal to phi of R1, phi of R2 minus phi of R3. Basically, all the operations on the right hand side are really operations that are happening in this world. Because you're multiplying two elements in S, you're subtracting two elements in S, etc., etc. Whereas here, the thing inside was happening in the R world. So this is a nice map in the sense that whether you do the operations and then apply phi, or you apply phi and then do the operations, the answer should not change. Okay, and naturally these are called homomorphisms. I mean, this is the same thing you had done in groups, and you were basically saying that in groups I want somehow the structure preserving maps from one group to the other. And here, instead of groups, you are working with rings. These are structure preserving maps. So once you have that, you can now define this thing called the kernel, just like you did for groups, which is what are all those things that got mapped to 0. Okay. And like in groups, the kernel seems to have a lot of nice properties. Here are some basic properties. If A and B are in the kernel, notice that A plus B in the kernel, A minus B is in the kernel, AB is in the kernel, etc., etc. So it seems to have all the necessary things, or somehow it seems to have the useful thing. It behaves like a subgroup, like it did in the group world. Here it sort of behaves like a subring. Okay, but it has one other really crucial property, which somehow you don't experience it at the group level, but you experience it here, which is, suppose A happens to be an element in the kernel and R is any arbitrary element in the ring. I'm not expecting R to be in the kernel at all. Then you have that AR is an element in the kernel. Because phi of AR equals phi of A times phi of R. And phi of A is 0. So you don't particularly care about what phi of R is. It's 0 times something, so it's going to be 0. Okay. So just like for normal subgroups, we were saying that, whatever this G inverse happens to be in the kernel, there was one additional property that you had there. This is the analog of that. This is the this is the additional property you get when you're talking about kernels of ring homomorphisms. Okay, and this has a name. One might say the name is not ideal, but this is what it's called. You say that a particular subset, this is like the analog of what a normal subgroup was for a group. And this is the analog of that. So a subset is called an ideal. A subset of R is called an ideal if it looks kernel-like in some sense. Like it has the property that whenever you take two elements in your ideal and you add them or subtract them, they should be in the ideal. And secondly, if you take something in the ideal and any other thing, their product happens to be in the ideal. Okay, let's just take some examples to get a sense of things. So for example, if your ring was the set of all integers, so one ideal is basically take all those integers that are all divisible by 7. Okay, notice that whenever two numbers are divisible by 7, whether you add them or subtract them, they'll continue to be divisible by 7. And when you take a number divisible by 7 and multiply with some arbitrary number, it's still going to be divisible by 7. No surprises here so far. Okay, but actually it turns out that you can take this set and think of it as a kernel of a suitable map. Okay, which is, if you think of this map from integers to this set of 7 elements, where you add, subtract, and multiply stuff mod 7. What are the things that go to 0? basically all the terms that were divisible by 7 would be mapped to 0. So in some sense, this I is the kernel of this map. So so in some sense, it's like ideals are kernels is what I'm trying to get to. Okay, let's look at one more example, which is here the ring is the set of all rational polynomials, say. Okay, and my ideal is going to be, let's take all those polynomials such that when I evaluate it at 7, I get 0. Okay, notice that two such things in this thing, if I add them up, of course, they will continue to evaluate to 0 at 7. And similarly, if I multiply f with any other polynomial and evaluate it at 7, just because of the fact that f of 7 is 0, the product will also be equal to 0. Okay. Can you come up with a suitable homomorphism such that this is a kernel?
So like, instead of sending it to mod 7, you're sending it to this is x minus 7 or no, wait, sorry, all polynomials.
So it must be, I'm looking for a map that takes a polynomial and spits out something such that the kernel of that map is precisely what this set is. Okay, so let me just tell you what sort of map it is. Can you come up with a suitable map that takes any polynomial and spits out a number?
So you evaluate the polynomial at 7.
That's it. So you just take f and just evaluate the polynomial at 7. Notice that whether you add and then evaluate or evaluate and then add, it makes no difference. So the evaluation map is a homomorphism. And the kernel is precisely all those f's such that it got evaluated to 0. Okay, so these are just some examples. And in general, just like subgroups, you can talk about an ideal generated by a bunch of elements, which is a set of all elements of this type. Because if A1 is in the ideal, you are forced to admit that R1 A1 is in the ideal for every choice of R1. That's one of your conditions. And similarly, any sort of sums of things in the ideal must be in the ideal. So this is just a notation to say that the ideal generated by a bunch of elements. Okay, now you can talk about what quotient rings are. Okay, so if I was an ideal in R, you can now talk about these coset-like things. Okay, which are things of these are sets that look like A plus R, where R happens to be in I. Okay, so it's just this is like a coset of I in some sense. And the cool fact about it is that, like you have in groups, you can sort of say that A plus these two cosets will be equal if and only if the difference happens to be in the ideal. Just like in groups, you said that AH equals BH if and only if something like whatever, B inverse A happens to be in the subgroup or some such thing like that. Okay, so we will use the notation A equals B mod I to basically mean that their difference is an element in I. So recall, this must be very familiar to you. There are times when you will say 42 equals 2 mod 10. That was equivalent to saying that if you take their difference, it's a number divisible by 10. Okay, so this is just a general setting that you can make whenever you're dealing with any sort of idea. And here's the fun fact, is that turns out you can add, subtract, and multiply things here. You can define an addition operation on these cosets and a multiplication operation on these cosets so that these cosets start behaving like a ring. Okay, so that is whenever you have a plus I and b plus I, you just define this to be a plus b plus I. Okay, and similarly, when you have a plus I times b plus I, I'm going to define it to be a plus b times I. Okay, I mean, this one needs to justify this, because you could say, well, if I took one particular element, maybe I took a plus R1 and you took some other, b plus R2 or something. So it shouldn't be the case that depending on what R1 and R2 I choose, the answer I get is different. One needs to show that this is a well-defined operation. Okay, now it's a very simple proof to say that this is a well-defined operation, which is that suppose someone took an arbitrary element of a plus of this guy and some other arbitrary element of this guy. I want to claim you will only get an element of this guy. You will not get anything else. Now, why is that? Suppose it was a plus I1 and this was a plus I2. What is the product going to be? It's going to be AB plus AI2 plus BI1 plus I1I2. Notice this is an element of I because I2 is an element of I. This is an element of I because I1 is an element of I. And this, both of them are elements of I. So therefore, this entire thing is an element of I. So that tells you that it doesn't matter which one you chose, you will end up with the same, whatever, coset. Okay. So basically, if you have a ring and you have an ideal, you now have a way of creating a new ring. Okay. And that ring is what is called a quotient. And this is something that you have done, earlier. For example, when you say integers mod 42, sometimes it's written as z mod 42z. That is, you are saying, let's take integers, but only look at its residue modulo 42. We'll add and multiply things appropriately. Okay, there 42z turns out to be an ideal in z, which is the set of all numbers divisible by 42. And if you look at its quotient, each of these things of the form 7 plus I basically refers to all numbers whose remainder mod 42 equals 7. So you naturally had an addition and multiplication based on that. And similarly, the complex numbers were things of this form, where you're literally saying that two such expressions are the same mod t squared plus 1. To basically mean their difference is divisible by t squared plus 1. We were doing it by saying whenever you see t squared, replace it by minus 1 or something. But that's the same thing as saying when you take its difference, you are ignoring any multiples of t squared plus 1 because in your mind, they are all 0. So this is basically what we were doing. It's just that we hadn't formalized what precisely it meant to write down an expression of this form. But now hopefully you know what these expressions mean. Okay. So, quotients are a very, very important concept in almost all of dash theory. Whether it's ring theory or group theory or field theory, whatever. These quotients just keep coming up. They're fundamental properties to study. And it's one of these things that you get better as you try more and more examples. So what I will try to do before the next lecture is put up a bunch of quizzes on Academy, just to get comfortable with various examples of ideals, various examples of quotients, many of which will be things that you're already familiar with. And hopefully that, you start appreciating these new constructions of rings, etc. And if people want to, maybe try out one example right away to get comfortable with it, I would suggest the following. So just like I was saying that ideals correspond to normal subgroups. Okay, see if you can devise a multiplication operation on cosets of a certain subgroup. And it will turn out that if the subgroup was a normal subgroup, the cosets actually have a group structure on it. You can multiply cosets and divide cosets, but this is something you can do only when you're dealing with a normal subgroup. And this is one other reason why normal subgroups are so awesome. Ideals are the normal subgroup analogs of rings. So just like there are ring quotient of one ring by an ideal, you can talk about a quotient of a group by a normal subgroup as well. It's something that I never went into because we never used it in part 1 of the course. But these ring quotients are something we're going to use quite a lot. So I'll put up a bunch of examples for you to just get familiar with these things. So yeah, I think today's lecture was probably a lot to take in. But as long as you are sort of familiar with the overall idea, that's good enough. I mean, the details are something that once you become more familiar with quotients, the details of the Schönhage-Strassen algorithm, etc., will become evident to you. But I would focus on, let's try to understand quotients and so on in the next lecture and stuff, because that is something we'll just keep on using. It'll keep on showing up in part 2 of the course. Okay, cool. So let me stop here and maybe just take questions before we break. We're already a little past time. Yeah.
So this general idea of quotienting, like, is it like wherever it's used, it's trying to say we already are working with this space and we want to now start saying something like, oh, let's just say these bunch of two like separate like elements, let's just say that they are actually the same thing.
So in some sense, quotients try to do the following. It's maybe best to describe in terms of a homomorphism. Suppose R was some ring and S was some other ring. Okay, so I have a map that goes from this ring to this ring. Okay, now there's a whole bunch of things that got mapped to the same element here.
Right, yeah.
Right, one of these elements was the 0, and this set is the kernel. But you can also talk about, okay, things that got mapped to, I don't know, 4, or things that got mapped to something else or whatever. Sure. So if you want to basically say, look, I don't really want to distinguish between things that got mapped to the same thing. Okay, I in my opinion, if they got mapped to the same thing, they are the same object. I don't want to distinguish them. Then once you relax your definition of distinctness, the resulting structure is the quotient of R with the kernel of this map.
Right.
It's like saying that things inside the kernel, you're not really distinguishing. They're the same.
Yeah, I think like, I mean, I'm just connecting this, like, so with like whatever little topology I studied. So when you're trying to define things like a torus, so it's like you basically like take a rectangular sheet, you want to say that the top line and the bottom line are the same. So I think formally the way you do is with
right. Exactly.
And the left and the right are the same.
Yeah. So I mean, intuitively, it feels like, look, if you don't particularly care about the distinctness between things that map to the same element, it feels like whatever structure you have on the left-hand side is basically the structure S. Right? I mean, to be more precise, it's the image of the map phi. And turns out there's a lot of truth to this statement. It turns out that the right quotient, if you set up the right quotient, it turns out to be isomorphic to the image. This is also called the first isomorphism theorem or something. And this is also something that you would have done in linear algebra. Like you have a linear transformation from one space to the other space. Then the quotients in some sense are basically what you get on the image. I don't know if I'm helping people who have not encountered this as much, but this is basically what quotients are supposed to do. The point of quotients is like, you somehow want to condense your information that you have and try and work with a slightly different object where you're losing some information. So this is something that you've also seen when we dealt with block kernels and stuff. If you have a block system and you are saying, let's instead look at G acting on the blocks as opposed to the individual points, it's almost like you're quotienting out whatever happened inside each block. So there also, I didn't use the word quotients, but that's what was happening there. So yeah, so it's a sort of fundamental object. And so this is the main definition per se. Like if you're willing to ignore multiples of something, then you say LHS equals RHS modulo t squared plus 1. Okay, and we'll deal with this a lot more. It will allow us to somehow make slow progress by saying that modulo a few terms, we have gotten it right, and so on, and we'll slowly try and make progress in many such situations. Okay, I mean, okay, I'm sort of just like sort of rambling, but things will hopefully become clear in the next few lectures. Okay, cool. So then we'll meet on Tuesday.